Every single time you send a text, or stream a movie, or just, scroll through your social media feed, you're basically commanding a massive army of billions of tiny little switches. And they're all speaking a language that has only two words, on and off. That's binary. And its simple math is the invisible force that's shaping our entire digital world. It sounds completely impossible, right? I mean, how can just two little symbols run everything from a simple calculator app on your phone to the most complex artificial intelligence? Well, that's the fascinating puzzle we're going to solve today. We're about to find out how pure elegance and simplicity can create some incredible power. So it all comes down to a really simple difference. We humans, we count in what's called base 10. Probably because, well, we have 10 fingers. It just makes sense. But computers, they're way simpler. They only have two states they can work with. An electrical circuit is either on or it's off. And that's it. A 1 for on and a 0 for off. And the absolute fundamental atom of this whole digital universe is the bit. Yeah, every photo you've ever taken, every song you listen to, it's really just a massive, intricate tapestry woven from these simple little ones and zeros. You can think of it as the DNA of all digital information. Okay, so if a computer only understands on and off, how in the world does it do something complex, like, say, calculating a rocket's trajectory? Well, the answer is going to feel surprisingly familiar. It uses the same basic rules of arithmetic you learned back in school, just with a much, much simpler alphabet. Let's start with addition. What's so cool here is how much this looks like the math you already know how to do. Let's add 101 and 011 together. Starting all the way on the right, 1 plus 1 equals, well, not 2. In binary, the number 2 is written as 10. So we put down the 0 and we carry the 1, just like you would in regular math. We do the exact same thing for the next columns and voila, our answer is 1000. See, the method is the same, you just have fewer digits to worry about. All right, addition is simple enough. But what about something that probably gave us all nightmares in grade school? Long division. You might be shocked to hear this, but in binary, it's actually easier. Seriously. Ready to see why? So let's divide 10,10,101 by 11. We start just like regular long division. Can 11 go into 1? Nope. What about 10? Still no. But it can go into 101. And here's the beauty of binary. The answer is always either 0 or 1. There's no guesswork. In this case, it's 1. So we write that down, do the subtraction, and find our remainder. Okay, next up, we bring down the next number, which is a 0, making our new number 100. Can 11 go into 100? Yep, it can. So we put another 1 in our answer, do the subtraction, and we're left with a remainder of 1. It's just a simple, repeatable process. You kind of get into a rhythm with it. And for the final step, we bring down that last 1, making our number 11. Well, 11 goes into 11 exactly 1 time. We add a final 1 to our answer, and we are done. No remainder. So 10,101 divided by 11 is 111. It's just a great example of the elegant simplicity of binary math. But what happens when the math gets messy? What if you ask a computer to do something impossible, like divide by 0? In the early days of computing, this was a huge, huge problem. Different machines would give you completely different answers, which led to total chaos and really unreliable software. As Professor Kahan puts it, anarchy threatened the entire world of computing. I mean, just imagine writing a program that works perfectly on your computer, but then gives completely different wrong results on someone else's. This was the reality, and it made building reliable software an absolute nightmare. So to solve this massive problem, the industry came together and created a universal rulebook. It's called the IEEE 754 standard. The best way to think of it is like the official rules of the road for computers. It makes sure that every single machine, no matter who made it, speaks the exact same mathematical language and handles these tricky situations in the exact same way. Now, one of the smartest parts of this whole standard is how it deals with dividing by 0. Instead of just crashing the whole program, the computer returns a special value, infinity. And this is a total game changer. It lets the program keep on running while still letting the user know that, hey, something a little weird just happened. And for things that are truly mathematically impossible, like dividing 0 by 0, the standard gives us NaN, which stands for not a number. It's basically the computer's polite way of saying, I have absolutely no idea what you're talking about, without throwing a digital tantrum and shutting down. Of course, computers aren't infinite. They have a limited amount of memory to work with. So when a calculation produces a number that's just too big to store, we get something called an overflow. It's kind of like trying to write a whole novel on a single sticky note. It's just not going to fit. The IEEE 754 standard gives us a way to handle this gracefully, which prevents the whole system from crashing. This table here is a great little summary of these rules. For all of these weird, undefined operations, the standard gives us a consistent answer, NaN. And it's this predictability that allows us to build the complex, reliable software that works the same way for everyone, everywhere. So what's the big takeaway from all this? Well, the entire digital world, with all of its mind-boggling complexity, is built on the super simple, elegant foundation of binary math. And for all the messy, unpredictable parts of reality, we have the IEEE 754 standard, a silent guardian that makes sure our digital world isn't just powerful, but also incredibly reliable. You know, we've really only just scratched the surface of the hidden language of computers. Binary arithmetic is the foundation, sure, but what other simple, powerful rules are out there quietly shaping our digital lives? What other elegant solutions are just waiting to be discovered?